At the end of the 1960s, while the superpowers of our planet were preoccupied with escaping Earth's gravity and reaching the moon, 900 million kilometers away, a small, distant comet fell foul of a much larger gravitational force. The 5-kilometer wide body had probably been flung inwards from the Kuiper belt surrounding the solar system, but instead of spiraling around the Sun's vast gravity well, it passed close enough to Jupiter to be captured in orbit around the gas giant. From then on, the comet's fate was sealed, but it would be another 2.5 decades before it eventually met its end. Shoemaker-Levy 9 was named after the scientists who first spotted it in 1993. But by then, it was no longer a single icy body. It had already broken up into a series of fragments, ranging from hundreds of meters to up to 2 kilometers across. Simulations revealed that the comet had been ripped apart by Jupiter's gravity a year earlier, when its orbit had brought it within just 40,000 kilometers of the gas giant's cloud tops. The next orbit, the researchers predicted, would bring the pieces on a collision course with the planet. And so in July 1994, under the watchful eye of ground and space-based telescopes, the pieces of Shoemaker-Levy 9 impacted Jupiter at over 200,000 kilometers per hour. Over a period of 6 days, there were 21 separate impacts, releasing energy equivalent to 6 million megatons of TNT, each collision producing a fireball that rose up to 3,000 kilometers above the Jovian clouds. And despite the gas giant's fluid outer surface, the scars from the impacts remained visible on Jupiter's surface for months after the event. The largest of these scars was almost the same diameter as the entire Earth, and for a time they were more visible than the planet's famed red spot. Indeed, for many years after, Jupiter experienced chemical and structural changes as a result of the comet's near miss and eventual demise. Within the planet's atmosphere, new chemical species were produced by the violent collisions and persisted for many years. The changes to Jupiter were surprisingly prominent and long-lasting, considering the small original size of Shoemaker-Levy 9. The fact that the comet didn't impact directly onto the surface, but instead experienced a near miss, undoubtedly helped to shape its eventual impacts. But what if the interplanetary traveler had been larger or denser? What if it had approached from an angle that would have preserved its fragmented orbit for longer? Then, we might not have witnessed the destruction of a satellite, but rather the genesis of a new ring system around Jupiter. It may seem far-fetched, but this is almost certainly how Saturn obtained its rings less than 100 million years ago, and there is growing evidence that our own planet turned a near miss into a glittering accessory, at least for a time, some 450 million years ago. And the story of how the Earth came to have rings, what happened to them, and what they did for our world is a tale that spans tens of millions of years, almost the entire Ordovician period, and may well have changed the course of animal evolution forever. Saturn's rings would fall apart without their shepherd moons, such as Prometheus, Pandora, Pan and Daphnis, keeping the dust, debris and particles from flying off into space. And indeed, without protection, your data can also disperse all over the internet, which is where Surfshark can help. Surfshark's VPN can keep your identity private and protected when online, and also protect you from the security dangers of public Wi-Fi. I'd been aware for years that I should have been using a VPN for security before finally signing up, but I've had great peace of mind ever since I did. With Surfshark, you can use an unlimited number of devices, and as well as the security benefits, the VPN is also great for accessing the streaming libraries of other countries. I spent a lot of time in both Spain and the UK, and there's nothing worse than being blocked from the next episode of your series if you get caught in the wrong country. And of course, you can also peek at what others are watching around the world as well. So, head to surfshark.com/HOTE or use the code HOTE at checkout to get 4 extra months of Surfshark VPN. Thanks to Surfshark for supporting educational content on YouTube. For the residents of Barwell in Leicestershire in England, Christmas 1965 came with a bang, followed by a thud and thousands of pounds worth of damage. It started, appropriately enough for Christmas Eve, with a bright light in the sky, but this star didn't hang in place for long. It streaked, a shooting star that heralded its coming with a shuddering sonic boom. Moments later, countless bangs and crashes sounded across the village and surrounding fields as the Christmas visitor fell to earth. But this was no heavenly messenger. It was a meteor, which had travelled millions of miles before tearing through the Earth's atmosphere and breaking into hundreds of pieces. Shortly after the brief sound and light show, carol singers making their way through the town noticed gravel-sized pieces crunching underfoot, but thought nothing of it. It wasn't until the sun rose on Christmas morning that the extent of the meteorite fall was revealed. Fragments of rock had crashed into the tarmac, leaving pits and craters behind. One piece even smashed into a brand new car, and when the owner tried to claim for the damage on his insurance, the company told him they couldn't pay, since it was caused by an act of God. Soon, word got out about the remarkable rockfall, and over the next few days, Barwell was inundated with people hoping to find a piece of fresh space rock for themselves. Money was offered for meteorite fragments, and Barwell experienced its own mini gold rush for this exotic rock. All that searching helped to confirm the Barwell meteorite as the biggest ever seen to fall in the UK. In the end, more than 40 kilograms of space rock was recovered from in and around the village, originating from an asteroid which predated the Earth itself at around 4.55 billion years old. Of course, today, finds like this are rare and valuable. Indeed, a nearly 1 kilo chunk fetched £8,000 in auction in 2009. But there was a time in our planet's history when rocks just like the Barwell meteorite may have been much, much more common. The Thorsberg quarry near Kinnekulle in southern Sweden produces fine limestone for flooring, tiles and architectural stone. The rock dates to the Ordovician, when calcium carbonate precipitated out onto the warm, tropical sea floor. But in 1988, workers at the quarry found something unexpected when they sliced open their reddish rock. Alongside the usual shelly fossils, there was a large chunk of a different kind of stone. Blackish green with a glassy, flaked outer edge, geologists soon realized that this intrusion was as exotic as they come. It was a fossil meteorite, just like the pieces that rained down in Barwell, except this rock had fallen while the Thorsberg limestone was still being deposited, 467 million years ago. This remarkable discovery sparked a search for more of the same, and over the next decade, researchers found a total of 40 fossil meteorites in this quarry alone, over an area barely larger than a football field. Unlike the Barwell rocks, which are numerous because they all came from a single fragmented meteor fall, these space rocks were scattered through the different strata of the Thorsberg limestone, without any evidence of the meteorites having been eroded out and redeposited. And dating of the limestone layers surrounding the exotic rocks show that they fell at various times over 2 million years, in at least 12 separate rockfalls. The majority of them are small, and together they total less than 8 kilograms, but it is their sheer concentration that makes them remarkable. At current rates of meteor fall, you wouldn't expect more than 1 or 2 rocks in an area the size of the Thorsberg quarry. So to find 40 meteorites in just 2 million years, something out of the ordinary must have happened. And not only that, but every single extraterrestrial rock trapped in the Swedish limestone appears to have the same original chemistry. In general, meteorites are classified as one of 3 bulk compositions. Iron, thought to be derived from the cores of ancient planetesimals. Stony, derived from those planetesimals' crusts and mantles, or from smaller rocks that never developed an iron core. And stony iron, which are a combination of the two, coming from the core mantle boundaries of now destroyed planetesimals. Among the stony meteorites, there are finer subdivisions, distinguished by the texture and chemistry of the minerals that make up those extraterrestrial rocks. And among those, the so-called chondrites are the most numerous. They are made up of tiny fused spheres, which represent individual droplets of solidified rock which accreted early in the solar system's history. The chondrites themselves are further distinguished by how much iron they contain. Iron-rich specimens are called H chondrites, for high iron, while L chondrites have low concentrations of iron, between 4 and 10%. And the chemical similarity of these rocks, regardless of where or when they are found, implies that they all originated from the same place. In fact, scientists consider it likely that they all originate from the same original asteroid or planet. Indeed, today, around 80% of all meteorites that fall to Earth are L chondrites, as was the Barwell meteorite and the distributed Ordovician rockfalls. And so all of this evidence points towards a startling conclusion. All of these rocks may be the lingering debris from an ancient cataclysm that saw an entire planet shattered into millions of pieces. This planet, dubbed the L Chondrite planet, would have begun much like our own. Roughly 4.5 billion years ago, in a thin disk around our sputtering newborn sun, dust consolidated into grains, which accreted into first pebbles, then boulders, and ultimately into planet-sized rocks that became rounded by their own rotation. Among these would have been the Earth, Venus, Mars, and Mercury, as well as Theia, which would ultimately collide with the Earth to create the Moon. But there must have been countless other rocks and baby planets swinging around the Sun on chaotic orbits, tugged this way and that by the shifting gravity of their larger cousins. The early solar system was a dangerous place for a baby planet, and impacts between these semi-molten planetesimals would have been common. Like water balloons colliding mid-air, their combined momentum would have sent droplets of iron-depleted molten rock spraying through space, where those droplets would freeze, accrete, and begin the process all over again. Indeed, it was only after a few more million years, when the hottest radioactive elements became depleted, that the final accretions of molten droplets wouldn't have remelted. Instead, the frozen droplets kept their shape as chondrules and became fused together, at least in the planetesimal's outer layers. 100 million years afterwards, the small L chondrite planet, with its gravelly texture and uniform chemistry belying its tumultuous past, would have cooled sufficiently and found a safe enough orbit for it to stand the test of time. And so we think it remained for roughly the next 4 billion years. But of course, nothing is safe forever, because around 500 million years ago, this unassuming planet met a catastrophic end in an event whose effects would be felt across the inner solar system. Scientists believe that the L chondrite planet would have resided somewhere between the orbits of Mars and Jupiter, within what is now the asteroid belt. However, as the giant planet Jupiter lunges around the Sun, its gravity can fling smaller objects off upon unpredictable orbits, wreaking havoc in collisional chain reactions. This is how many asteroids in the belt came to be, and is the source of much of the interplanetary debris that clutters the inner solar system today. The L chondrite planet would have done well to avoid this fate for 4 billion years, but it eventually succumbed, and either the whole planetesimal or many of its fragments were hurled inwards, towards the Earth. And had this ancient planet, or one of its larger fragments, collided directly with the Earth, the result would have been catastrophic, similar to the dinosaur-killing impact at the end of the Cretaceous. But we see no extinction event, no single calamitous episode in the planet's geological record. Instead, it seems, the Earth received a drawn-out pummeling. The Thorsberg limestone records a pulse of small scattered meteorites, all of the same composition but spread out over 2 million years. And this isn't the only evidence of impact from this time. All around the world, the researchers find fossil impact craters that suggest that during the early Ordovician, the flux of space rocks to Earth was 10 to 100 times higher than it is today. And it wasn't just full-sized meteorites either. Micrometeorites are constantly raining down on our planet. Unnoticed, but for the characteristically extraterrestrial particles, they scatter like salt through accumulating sediments. Like their larger counterparts, the flux of micrometeorites is relatively constant through time, except throughout the Ordovician, it was as much as 10,000 times higher than at any other point in history. This comparatively torrential rain of space dust began around 467 million years ago and lasted, albeit diminishingly, for some 30 million years. Now, the key thing to know is that the way extraterrestrial material is delivered to Earth hasn't changed over the last 500 million years, and there is no known mechanism that can keep sending meteors and their associated debris across interplanetary space so consistently and for so long. Not only that, but the drizzling bombardment that our planet received does not seem to have affected our planetary neighbours. Naturally, our sampling is limited, but there is no conclusive evidence of Ordovician-age cratering or meteoritic bombardment on either the Moon or Mars. If meteorite material had been flung out of the asteroid belt and in towards the inner solar system, then of course there's an even chance of that material hitting any of the planets within that neighbourhood. That only the Earth should be affected, while the other bodies were spared, seems vanishingly unlikely. How then are we to explain the uniquely targeted but drawn-out assault that our planet received throughout the Ordovician? It is clear that there must be another twist at the end of the L Chondrite planet's story. And in solving this mystery, a crucial piece of evidence came to light in 2024. The 100-fold increase in meteorite falls during the period in question means that there are some 20 or more impact remnants preserved from this time, in locations ranging from modern-day Canada to Australia, India, and Northern Europe. Today, those locations are scattered across the globe, but when researchers reconstructed plate motions over the last 450 million years to map the position of the Ordovician continents, they revealed a remarkable pattern. These impact craters weren't distributed randomly, as you might expect from an interplanetary bombardment originating in the asteroid belt. Rather, they were concentrated in a band around the equator. And it is this, along with the other seemingly inexplicable features of the Ordovician meteorite bombardment, that has led scientists to a single, surprising conclusion. All of this meteorite material was derived from a ring of rock and dust that encircled the Earth. And so this may well have been the fate of the L Chondrite planet. Either the whole planet, or a large fragment of it, would have been launched out of the asteroid belt by the orbital chaos within that region of space. It crosses the interplanetary distance, making a direct line for the Earth, but instead of colliding, it misses by the narrowest of margins. Had it been further away, the fragment may have been captured and ensnared into orbit as a second moon, similar to how Mars acquired its 2 moons. But in this scenario, the L Chondrite fragment comes closer. So close, in fact, that the Earth's gravitational forces rip it apart, just as Jupiter had done for Shoemaker-Levy 9. Orbital calculations place the L Chondrite planet's near miss at somewhere less than 15,000 kilometers, which is less than 4% of the distance to the Moon and well within the orbits of our modern geostationary satellites. The breakup of the rocky planetesimal would have left behind a scattered field of debris, spinning around the planet with its original momentum, forming a ring system like that which adorns Saturn today. The difference is that this ring would be made of rock rather than ice, and would be somewhat more compact, likely missing Saturn's ring's characteristic stripes. Over the next 40 million years or so, the pieces that make up the ring would slow and descend, caught by the Earth's tenuous upper atmosphere and deorbiting like decommissioned satellites. meteorites large and small would rain down, as ever so gradually the rings disintegrate and fall to Earth. While they would have persisted, however, the sight must have been a spectacular one. From the surface, a darkened arc of dust and debris would hang motionless in the sky, shading the sun during the day and reflecting it during the night, lighting the night sky in a way similar to, but more intensely than, the full moon. At the equator, the ring would be barely visible as a thin line passing directly overhead. At the poles, it would hug the horizon, but in the middle latitudes, the debris ring would permanently dominate a large swathe of the sky, changing only as the Earth's shadow swept across its surface. This all may seem like science fiction, but at the moment it is the only explanation that scientists have found to tie together all of the conflicting meteorite evidence from this time. Accessorized with a rocky debris ring, our planet would have looked remarkably alien, even while the ancestors of all living animals and plants thrived on its surface. But a closer look at the geological record reveals that the surface of the planet itself was far from familiar. In ways both unrelated and also perhaps heavily influenced by the planet's odd cosmic events, throughout the Ordovician, the Earth was also experiencing one of its most extreme and bizarre phases. A phase that would have rendered the planet at the center of those rocky rings all but unrecognizable. The wind was the first to arrive. Palm trees whipped and bent at infeasible angles, while the branches of tropical hardwoods and pines were ripped from their trunks and sent crashing through the village. Rain fell and soon became a deluge, turning the red earth underfoot to sticky mud and submerging everything as water pooled faster than it could drain. Houses were cut off from one another, and the souls who huddled inside them isolated by several feet of rushing water hammering past their doors. Sails furled, lines taut, and cargo strapped with every available piece of rope as the 3 wooden ships moored offshore were tossed about like toy boats. Gradually at first, and then, all at once, Christopher Columbus's flagship disappeared beneath the tempestuous waves. When Columbus set out to discover the Americas at the end of the 15th century, he was already an accomplished seaman, but he couldn't know what awaited him on the other side of the Atlantic Ocean. Throughout his initial voyages, the explorer and his fleets visited the Caribbean islands, including Hispaniola, home to modern-day Haiti and the Dominican Republic, where he encountered the native Taino people and set about establishing Spanish settlements to stake the nation's claim on the discovered lands. But the Taino knew much about their homelands, the Columbus did not, and while he could only helplessly watch as 2 of his 3 ships shattered and sunk, the natives had long abandoned the coast and retreated to the mountains. They had recognized the signs of the oncoming storm, which they attributed to their vengeful god Huracan, and had sought shelter far inland. But to his credit, Columbus swallowed his pride and took the lesson from the Taino, and 7 years later, when his fleet was passing the new settlement of Santo Domingo, he saw the changes they had taught him to watch for. A reddened sun, higher swells on the sea, and the irregular behavior of animals more sensitive to the natural environment than man. Columbus sailed his ships to the west of the island to protect them from the worst of the storm, but another Spanish fleet was not so lucky. When the storm struck the next day, the Taino's god claimed 25 of their 30 treasure-laden ships, along with the lives of 500 sailors and untold numbers of slaves. The wisdom of the Taino came from their experience, since the island of Hispaniola, along with all of the Caribbean islands, have weathered storms like this since there have been islands in this part of the world. Their god, Huracan, eventually gave its name to these uniquely destructive storms in the Northern Hemisphere, and hurricanes continue to shape the history of the Western Atlantic. Warm temperatures over the tropical ocean, combined with large-scale circulation within the atmosphere, conspire to brew unstoppable, spiraling storms that wreak havoc across all that stand in their path. Island nations are especially cruelly affected, since their small land masses do little to diminish the storm's energy. And indeed, as global temperatures continue to soar in modern times, even the Taino's wisdom may not be enough to withstand the fury of Hurricane. And yet, however destructive the Atlantic hurricanes may become, they will pale in comparison to the tempests that ripped across the Earth beneath the shadow of its transient rings 450 million years ago. By this point in the Earth's history, the stable centers of many of our modern continents were already established. The large continent of Gondwana dominated in the southern hemisphere, stretching from the equator to the South Pole and containing much of what is now Africa, South America, Antarctica, and Australia. The rest of the continents, Laurentia, containing modern-day North America, Baltica, and much of northern Europe, and Siberia, now found in the center of Russia, was still distinct, separated from Gondwana by some 8,000 kilometers. The Paleotethys Ocean lay in between, about twice the width of the modern Atlantic, but also studded with many smaller islands around the edges of the larger continents, like the Caribbean writ large. These so-called ribbon microcontinents were a product of the state of plate tectonics during the Ordovician. Plates move over the Earth's surface constantly. Sometimes their slow, grinding movements crush continents inexorably together. Other times, land masses are mercilessly ripped apart. But around 450 million years ago, all of the action was taking place in the oceans. At some distance from the existing continents, ocean crust subducted beneath ocean crust. Trapped water was released from buried slabs of rock, causing the crust above to melt, creating magma, which itself rose up and created new volcanic islands parallel with, but just behind, the subducting ocean trench. All along the trench, new island formation took place, forming an interrupted ribbon of land mirroring the larger continental edges. But with all land masses together south of the equator, there was nothing but featureless blue to the north. Ocean reigned supreme. Winds blew uninterrupted, diverted only by the Coriolis forces from the spinning globe itself, and beneath the surface, water currents followed suit. This panthalassic ocean was one of the Earth's great super-oceans, covering more than half of the globe, nearly double that of the Pacific Ocean today. Embarking north from the equator, an Ordovician submarine could travel some 20,000 kilometers under the sea, passing across the pole before they encountered land again. From the vantage of the planet's encircling ring then, the Earth would be a world of two halves, split almost perfectly by that alien rocky swathe. To the south, a tropical paradise of sparkling turquoise seas dotted with islands and smooth-edged continents. To the north, an empty expanse of deepest, darkest blue, whipped into huge swells and capped with white spray, but with no shore to break those towering waves. It's likely, however, that little of this remarkable vista would have been visible for long, for yet another swing of the Earth system pendulum conspired to make our planet appear utterly alien throughout this period. Building the ribbon microcontinents that edged the larger landmasses required immense quantities of lava, disgorged from the bowels of the Earth to flow over the sea floor and over previous flows until it eventually breached the water's surface to create new land. But molten rock wasn't the only thing that these volcanoes produced. With every eruption, and even between eruptions, the volcanic vents poured tons and tons of invisible carbon dioxide gas into the atmosphere. And there it behaved just as it does today, acting as a greenhouse gas, trapping incoming solar radiation and swaddling it close to the surface, heating the air, water, and land surfaces alike. Indeed, the late Cambrian and early Ordovician saw so much volcanism that atmospheric carbon dioxide levels soared, reaching levels higher than at any other time in the Phanerozoic, including today. With around 1 in every 200 molecules in the atmosphere being carbon dioxide, concentrations were some 15 times higher even than the modern post-industrial Earth. And so just as high concentrations of greenhouse gases today are contributing to elevated global temperatures and unpredictable climate, these extreme carbon dioxide levels would have sent temperatures soaring throughout the early Ordovician. Researchers estimate that on average surface temperatures reached 10 degrees Celsius higher than today. No ice could have survived under such sweltering heat, even at the poles, and any water that could have been sequestered there now flowed freely into the oceans, boosting sea levels and flooding continental shelves. Around the new volcanic islands at the continental fringes, shallow, sunlit seas were as warm as bathwater. But despite this, in reality, this was no tropical paradise. Heat translates to energy in the atmosphere, which must find an outlet somewhere within the claustrophobic shell of the planet's surface. Under such high temperatures, water evaporates from the sea surface at a terrifying rate, stuffing the troposphere with water vapor, building towering thunderclouds and raising the humidity to a stifling swelter. Torrential rain falls daily, but offers little relief from the torrid, sticky heat. Winds blow constantly, gusting from high to low pressure systems formed by the large-scale circulation of the atmosphere. And more heat means more energy, which means ever more powerful winds. And the hemisphere-spanning Panthalassic Ocean only served to reinforce the atmospheric tumult and brew perfect, never-ending storms across its surface. A seemingly endless expanse of water and uninterrupted Coriolis winds whipped storm clouds into cyclones thousands of kilometers wide. And with no land on which to release, these hurricanes build and build, tracking diagonally across the globe until eventually hitting higher latitudes, cooler water, and calmer conditions. Near the equator, however, where the young volcanic islands lie, amid shallow seas within the maelstrom's path, the bombardment would be relentless. Like the Caribbean islands, they would be exposed to the full force of the oncoming hurricanes, but would offer little in the way of resistance or moderation. The storm surges churn up the bottoms of their sandy seas, triggering devastating underwater landslides before hurling and stranding water, mud, and marine debris far inland. And the storms keep coming. For millions upon millions of years, hurricanes whip around the globe under the eerie shadow of a dusty planetary ring. This was particularly dangerous territory for an unbalanced climate system. With temperatures so high, there was a real risk of positive feedback in the Earth system causing a runaway greenhouse effect and sending the planet into an inescapable heat spiral. High temperatures evaporate more water, filling the atmosphere with heat-trapping water vapor and boosting temperatures further until rivers, lakes, and eventually the oceans evaporate away. Indeed, it's likely that something like this happened to our planetary neighbor Venus. Being situated that much closer to the Sun made it easier for greenhouse conditions to turn critical. But, thankfully however, this wasn't to be the fate of the Ordovician Earth, despite the colossal carbon dioxide concentrations. Instead of rising out of control, carbon dioxide levels and temperatures actually fell throughout this period, and scientists believe we have the Sun's youth to thank for our savior. "480 million years ago, the Sun gave out approximately 4% less light and heat, meaning that there was much less radiation available for the greenhouse gases to trap, therefore keeping the temperature rise extreme, but not inescapable. There were other factors at play, of course, among which the planet's rings were almost certainly a significant part. The shadow that this rocky band cast would have changed throughout each day, from season to season and across the millennia, but its cooling embrace doubtless had a tangible influence on the global climate and on the conditions that reigned down on the surface. And that was not all it did. As well as preventing a runaway climate catastrophe, the orbiting fragments of the L-chondrite planet may well have seeded a lasting change on Earth's life as well. For over the course of the Ordovician period, it's likely that our alien rings had a guiding hand in one of the Phanerozoic's biggest booms, and one of its biggest crashes. Sometime in the late Cretaceous, a fireball streaked across the sky and struck the Earth. But this wasn't the city-sized rock that would bring a cataclysmic end to the dinosaurs. This was a more modest, 1.5 kilometer wide asteroid fragment that impacted what would become southern Finland. And though it may not have been enough to bring about a global catastrophe, it was certainly capable of doing serious damage to everything within its fateful reach. At the moment of impact, rock was liquefied and vaporized, experiencing temperatures of up to 15,000 degrees Celsius and instantaneous pressures equivalent to that found at the center of the Earth. The asteroid itself was obliterated, and the collision carved out a crater some 23 kilometers wide and more than 700 meters deep. All around the impact site, the coniferous forests were flattened and set alight as a scorching fireball spread out from the center. Luckless dinosaurs, mammal ancestors, and insects alike were burned, battered, and buried by debris. When the dust eventually settled and the smoke cleared, the crater and its immediate surroundings were left sterile and steaming. No living thing, not even a microbe, survived this local cataclysm. Even as the seasons changed, it would be nearly 1 million years before this scar in the Earth cooled enough for liquid water to remain. Then, a lake began to pool in the basin, fed by rain and groundwater, but still hot and chemically corrupted by the altered rocks at its base. Nevertheless, life found a way back into the cratered wreckage. First came the microorganisms that could withstand high temperatures and acidic waters. Hydrothermal microbe communities, similar to those found around hot springs, could have turned the crater lake a rainbow of colors as they manipulated the water chemistry to their own ends. Over time, temperatures in the water cooled enough for the heat-tolerant organisms to be replaced by a more cosmopolitan community. Spores and pollen blown on the wind from surrounding vegetation helped heal the broken barren ground with fungi, lichen, and mosses, and the soil they could create. At first, the lake and its shores were tough places to eke out an existence, but more soil meant larger plants, grazing animals, and a succession of complex ecologies. Richer organic soils leach nutrients into the crater lake, and it becomes capable of supporting large populations of fish. But this succession does take time. Thousands or millions of years may pass before the scar fully heals, and the ecosystem it hosts will always be different from that around it. And this is a pattern that intelligent animals, humans, are able to exploit. The crater lake later becomes a hub for Bronze Age hunters who seek the animals that are drawn to the productive watering hole, and thousands of years later it is still a hub, but now for other human visitors seeking to enjoy the natural pleasures this diverse landscape offers. The town of Lapayavi grows on the lake's northern shore, supporting tourism and fishing, while the fertile soils of the diverse surrounding area are plowed for wheat, rye, and potatoes. In the winter, skiers visit, riding a ski lift that ascends the rim of a 77-million-year-old impact crater. And none of this would have been possible without the late Cretaceous impact. Had the rock not struck the Earth, then this region of central Finland would have remained unaltered ancient taiga forest, without any of the biological and anthropological richness that it now boasts. And so the impact may have been a calamity at the time, but wiping the slate clean and starting afresh allowed a more varied and productive ecosystem to grow in its place. In this way, impact events are unique. They are some of the only mechanisms capable of disrupting an ecosystem locally in both space and time. Crater-forming collisions of this size aren't large enough to affect the global environment, but they can make a big difference on a local or regional scale. Statistically, however, they don't happen often. Impacts like this can be expected somewhere on Earth every 2 million years or so. But 450 million years ago, in the Ordovician, such targeted ecosystem engineering would have been much more common, thanks to the planet's encircling ring. The extraordinarily high temperatures at the beginning of the Ordovician meant that none of the Earth's water was trapped in ice shelves or ice caps, and instead topped up the ocean reservoir. This, combined with the low relief of new volcanic islands, meant that sea levels were at their highest point for several 100 million years, and only continued to rise throughout this period. Water flooded the vast continental shelves, creating warm, shallow seas all throughout the southern hemisphere that were just a few hundred meters deep. This was a tropical paradise for marine life, of which the Ordovician boasted plenty. The shelves surrounding each of the smaller continents created distinct and separate habitats, allowing seafloor communities to adapt and diversify in response to the unique conditions each one offered. As a result, the Ordovician period played host to one of the most remarkable periods of biodiversification of the entire Phanerozoic. The Cambrian explosion, some 40 million years earlier, had seen the invention of most of the modern animal phyla. At this time, the major animal divisions were carved out based on fundamentally different body plans. The arthropods, chordates, echinoderms, mollusks, among others, taking their places on the stage of life. For example, the trilobites, who could trace their heritage back to the early Cambrian, had come into their own by the Ordovician. They diversified into nearly 5,500 species, within 56 families distributed unequally around the planet and adapted to an astonishing range of specialized lifestyles and habitats. New forms had highly developed eyes, on stalks, pillars, and with shaded brows to help them perceive danger all around in the water column. Many trilobite shells became better articulated, allowing the creature to bend and flex, which would help with both defensive poses and swimming through open water. And numerous other species developed spines, knobs, and other ornaments around their shells, which may have helped with sensing, giving traction in soft sediments, or even as a deterrent to predators. All of this helped them to succeed in a wide variety of marine environments. And indeed, they weren't alone. As well as this dominant group of arthropods, there were plenty more diverse and disparate marine groups on the sea floor and in its waters. Large, biologically constructed mounds, called bioherms, grew where ocean currents, nutrients, and sunlight favored them, constructed as they were from overlapping growths of algae, sponges, and colonial organisms called bryozoans. The echinoderms expanded to include many branching crinoids that rooted to the sea floor or swam freely through the water, as well as sturdy stemmed blastoids, now extinct. A related group of free-floating hemichordates became known for the chalk-like scrawls their fossils seemed to leave in slate, and were named graptolites as a result. They thrived during the period with over 40 different species, and mollusks zealously joined the fray as well, with countless species of clams, snails, and free-swimming cephalopods appearing and proliferating for the first time. And alongside these invertebrates were our own ancestors too. Chordates, defined by a central cord of nerves that would eventually manifest as a vertebrate's spinal column, begin to appear recognizably fish-like around this time, with eely conodonts known mostly for their teeth, and the first bony fossils of jawless armored fish related to hagfish and lampreys. And so whether in the water, in the seafloor sediment, or anywhere in between, the oceans teemed with specialized life, the likes of which had never before been seen on Earth. But why did it happen then? What was so special about this particular time? Oceans have been warm, seas have been shallow, and continents have been distributed at other times in the Earth's history, but those times have not seen the same remarkable diversification that defined the Ordovician. One explanation is related to the relative immaturity of animal life itself. Prior to this early stage of the Phanerozoic, there had been no mobile, macroscopic life to speak of, and so the marine environment had spent the preceding 4 billion years or so largely untouched by the biology that inhabited it. But that changed once animals started moving around. An influx of worms and other creatures burrowing into the sea floor disturbed chemical reservoirs for the first time, mixing them up and ultimately altering the chemical composition of the oceans and atmosphere. It's thought that this burrowing initially helped to release oxygen from the sediments, which would have oxygenated greater expanses of the oceans and offered more opportunities for energetic biology. Indeed, during the Ordovician, elevated oxygen levels are correlated with periods of greater diversification. However, at other times in Earth's history, pulses in oxygen haven't necessarily seen such a boost in diversity, so this can't be the whole story. Instead, researchers are considering the possibility that this unique phase of evolution could have been driven in part by the planet's unique accessory at this time: its rocky ring system. When the L-chondrite body experienced its near miss with the Earth, gravitational forces and subsequent collisions would have ripped it into countless fragments that remained in orbit around the planet. But these orbits wouldn't have been stable over the long term. Air resistance from the top of the atmosphere, plus other chaotic collisions within the ring itself, would have caused pieces of rock to frequently de-orbit and come crashing down to Earth. Indeed, it was these pieces that were found in the limestones of Thorsberg Quarry, but we can expect there to have been countless others. The larger among them would have struck much like the Finnish meteor during the Cretaceous, carving out craters in the Earth and obliterating themselves in the process. Like that Cretaceous impact, these collisions would have wreaked havoc on the local environment. Everywhere the rocks struck, water would be vaporized, all animal life eviscerated, and the crust locally shattered and superheated. It would have taken thousands of years for the area around the impact to recover, but when it did, it would be subtly different from the environment that had existed before. Perhaps the depth was slightly different, or the water chemistry, or the way the ocean currents flowed. But whatever the difference, it created new opportunities for the life that recolonized it. In this way, the minor but persistent impacts caused by deorbiting rocks from Earth's rings could have created a patchwork of new niches for animals to adapt to. The global environment wasn't significantly affected, but existing ecologies would have been constantly disrupted, leaving survivors to start again in new environments and forge new paths to success. There is evidence that the planet's ring system persisted for some 40 million years, and so local marine ecosystems could have been made and remade countless times within this period. Each new succession would create new species, which aren't entirely wiped out by the next impact, resulting in an overall biodiversity boom, the likes of which has not been seen before or since. However, this storm of success was not to last. While the rings may have been a boon to biology in the beginning, they may also have been instrumental to its demise by the end of the Ordovician, because no sooner had this Paleozoic biodiversity blossomed, it was struck down once again, and to this day, scientists aren't sure why. Throughout the early Ordovician, carbon dioxide levels, temperatures, and sea levels remained high. But, abruptly, around 445 million years ago, CO2 dropped and global temperatures plummeted, leading to a sudden glaciation and oceanic changes that would wreak havoc on the warm, marine Eden that had dominated for the last 40 million years. Sudden cold temperatures caused ice caps to grow over the part of Gondwana that lay over the South Pole, sequestering water as continental ice caused sea levels to drop, draining the shallow shelves at the edges of the land masses, drastically reducing the habitats for seafloor dwelling organisms. Even those who were spared exposure to the air would have found themselves subjected to ocean waters far colder than they were adapted to, as well as pulses of suffocating anoxia as ocean circulation changed. The result was catastrophic to the new, granular diversity of the Ordovician seas. Shallow water faunas were especially impacted, with many groups of brachiopods, trilobites, bryozoans and crinoids disappearing for good. Overall, with around 85% of all species, up to 60% of all genera, and over 100 of the newly founded families becoming extinct, the end Ordovician mass extinction ranks second in the so-called Big Five mass extinctions in terms of the percentage of marine families affected. Indeed, it was twice as damaging as the dinosaur-ending extinction at the end of the Cretaceous. While the link between glaciation, anoxia, and extinction is fairly clear, what's less clear is the cause of the glaciation in the first place. Some researchers have suggested a natural cycling of carbon dioxide through weathering and volcanic output, but the abruptness of the event causes problems for this explanation. It may be that biology had a role in its own demise, but other scientists have invoked more extraterrestrial influences to explain this remarkable event. One theory suggests that the Earth was hit by an energetic gamma-ray burst, released by colliding black holes somewhere close by within our galaxy. These damaging cosmic rays could have irradiated shallow water animals and created a photochemical haze in the atmosphere that brought on cooling and glaciation. But the evidence for such a dramatic, galactic event is lacking, and perhaps we don't need to look so far afield to find an alien agent of destruction. Perhaps it was orbiting Earth all along. The rocky debris from the breakup of the L-chondrite planet would have dispersed in a thin but wide ring around the Earth. While this ring would be all but invisible from the equator, elsewhere on the planet it would have been a significant and constant feature of the sky, following a similar arc to that of the Sun itself. As such, depending on the ring's density, it may have offered significant shading to the surface below, helping to regulate some of the greenhouse heating, and potentially, eventually ushering in a devastating ice age. Of course, there's still much we don't know about the ring system. How large it was, how dense it was, and how it evolved through time would all significantly affect the degree of shading and cooling it could cause, and consequently, how big a role it played in the Ordovician mass extinction. But the timing at least seems to be consistent. The heightened rate of L-chondrite meteors falling to the Earth begins around 467 million years ago, and the onset of the end Ordovician glaciation and extinction occurs more than 20 million years later. It's therefore possible that a small but consistent cooling effect could have accumulated over that period to help usher in the mass extinction. And there is one further possibility. Recently, researchers mapping the gravitational field throughout southeastern Australia found something big and unexpected buried beneath the surface. Across a region some 1,000 kilometers wide is an area of dense, compacted rock that appears to have been created by a gigantic planetary impact. The Deniliquin mega-impact structure, as it's known, consists of multiple overlapping crater rings, surrounded by hills that were wrinkled up by massive deformation. Overall, the structure is some 10 times wider than the Chicxulub crater left by the dinosaur-killing impact, and would have been created by a collision that released as much energy as 100 billion megatons of TNT, releasing catastrophic global tsunamis and sun-blocking dust clouds. And while the dating of the buried craters isn't particularly precise, it does cover the Ordovician, when the Earth's presumed rings dominated, and the ensuing extinction. And so is this Deniliquin structure related to the Ordovician glaciation and extinction? And was it a fateful product of Earth's transient ring system? Perhaps a larger fragment that escaped disintegration and persisted as a micromoon before crashing cataclysmically to Earth. A Ultimately, we still know too little about it, but it's a tantalizing possibility. Should we discover meteorite fragments of the right chemical composition embedded in damaged rocks of the right time period, then we would have our smoking gun to link the L-Chondrite planet to the Ordovician ring-bearing era of boom and bust. And so, while a rocky ring system around the Earth would have been a remarkable sight, both from the Earth and from space, those rings had the potential to deal fortune and fatality to life on our planet. They may have decided what animal groups lived and died, and thereby shaped the future of all animal evolution. You've been watching the entire history of the Earth. Don't forget to like and subscribe, and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.